In this video, I'll introduce some notes on the second law of thermodynamics for a general chemistry audience. So the second law of thermodynamics, one way to interpret it is the statement that the change in entropy of the universe is equal to the sum of the change in entropy of the system and surroundings, where entropy has the symbol S. So the change in entropy of the universe is equal to the sum of the change in entropy of the system plus the change in entropy of the surrounding and this for the most part is greater than 0. It can be equal to 0 temporarily, but it's going to be greater than 0 for the most part. So we've got some labels here. We've got universe, system, and surrounding. Notice there are 3 labels, but there's only 2 objects. One of the labels is the sum of the other 2 objects. So we have a system that can exchange information with the surrounding. And the system by definition is anything that you, the scientist, decide it is. If you're a physician, the system is your patient. If you're a barista serving coffee to somebody, the system is the coffee in front of you. If you are the mayor of a city, the city is your system. So the system is whatever you define it to be. If you're a dentist, the open mouth in front of you is the system. The surrounding is everything else. So there can be an interaction of information between the system and the surrounding. And we call the sum of these 2 objects the universe. So this is important. A common mistake is that students will think that there's 3 objects. That's incorrect. There's 2 objects, the system and the surrounding. If you're looking collectively at those 2 objects, you can say the universe. Okay. So now we're going to comment on the fact that the entropy of the universe is always increasing. And we know what the system is, and the system therefore is easy to measure. It's very difficult to measure the surrounding, so we're going to try and rephrase this term so that we can change the label from surrounding to system. So let a positive change in the entropy of the surrounding equal a negative change in enthalpy of the system divided by temperature. So essentially, notice here I've changed the label surrounding and system, and I've changed the sign positive and negative. The change in sign because of the change in label is apparent based on our definition here, because they have different directions. The system has the head of this arrow, the surrounding has the tail of that arrow, so the directionality is what leads to the change in the label of the variable from positive to negative upon changing the label surrounding the system. So a positive increase in the surrounding entropy is equal to a decrease, a negative change, in the enthalpy of the system divided by temperature, and here temperature has to be in units of Kelvin. Based on this statement, this implies that the entropy change of the universe, we can now write it, this expression here. So we're going to rewrite this expression. So I can say the entropy of the system again, which is this term here. And now rather than positive this term is equal to negative this term, so I can write negative this term. In doing this now, I've got the universe defined in terms of just the system. And I can say that this whole term is now greater than 0. If we multiply through by negative t, so we're going to take this expression, we're going to multiply through by negative temperature. We get negative t delta S universe, which is this expression here, equals, let's take this second term, let's hit it with negative t. Well, the negative t would cancel this negative and make it positive. And the temperature in the numerator would cancel the temperature in the denominator. And then I can multiply this last term by negative t, which would make it negative t delta S system. Which is greater than 0. So again, I took the term in the box, I rephrased it so everything is with respect to system. I multiplied through by negative t, so now I have this equation. And the last thing for me to do in this slide is just to make some definitions. So we call this term delta G, where delta G is Gibbs free energy. So we rephrase that as Gibbs free energy, and we've got enthalpy and then we've just got the product of temperature and entropy. So this form of the second law, it's essentially the same as this. It's one equation. It's just much more useful in chemistry. So I'll pause the video and we'll move on to the next content. Okay, we left off in the previous slide with this equation, which is a useful expression, a useful representation of the second law of thermodynamics for a chemistry audience. So change in Gibbs free energy is equal to the sum, where I'm not discriminating positive and negative values when I say sum. Sum of enthalpy considerations and entropy considerations, and if we're talking about the change in the universe, then this must be greater than 0. To move forward with this equation, we have to do away with these delta symbols. So let's strip this down of its delta symbols, and we'll just write G. So I'm just going to take away the delta symbol. G is H minus TS, and I'm going to replace the delta symbol with a D symbol, so I can write dG is dH minus dTs. So here D just means difference, deviation, or actually it means differential, but we'll see that differential here just means difference. Okay, so we've essentially just replaced this average change with this infinitesimal change because we're interested in the infinitesimal change. And there's a brief aside that will help us move forward. And the aside is on something called the product rule. We're going to have to apply the product rule over here because we have the product TS. Okay, so the product rule essentially says if you take a product, so let's say our product is AB. So if you take a product AB and you want to take its differential, you would have to ignore one of these variables and apply the D to the second variable, and then vice versa. So let's ignore A and let's apply the D to the B. So D only acts to its right. So by putting A to the left of the D, I ignore the effect of D on A. So A multiplied by D on B plus B multiplied by D on A. So that's our little aside. If we now apply this product rule to this expression, specifically to the DTS, then I've got dG is dH, but then I'm going to apply it to this equation here. So we have, let's ignore the T and apply the D to the S, and then let's add the next term, which is the S, and then we'll apply the D to the T. Now I have to add it because of this, but I have a negative here, so it's going to make the whole thing negative because I'm adding a negative term. And we'll call this equation 1. So let's call this equation 1. Now we're going to recall an equation that you might have seen before. If you haven't seen it before, it won't be a recall, it will be a note. So enthalpy, H, is total internal energy plus pressure and volume as a product. So typically you would look at the second law in the second sequence of a general chemistry class. Typically you will see this equation in the first sequence of a general chemistry class. So that's why I'm referring to it as a recall equation here. If we apply these as we've done here, notice that this equation is almost identical to this equation. If we apply these here, we would have dH is du plus dPV. So just like as we did here, and again we have a product, so we're going to apply the product rule. So dH is du plus VdP plus PDV, and let's call that equation 2. Okay, so we applied the product rule to this product here, and we were able to come up with equation 2. There's a couple of extra bits and pieces we'll need so that we can do something with this equation. So I'm just going to underline that to keep it separate. So we'll recall a few more equations that will be handy. So from a previous class, we have this term du, so the change in internal energy. We can write dH, no, sorry, I skipped ahead a little bit. This is the sum of heat and work. So this expression you'll recognize as the first law of thermodynamics, where we're going to assume that we can write heat is equal to dH, which we can under isobaric conditions, so constant pressure conditions. This is an equivalence that will hold. And we're going to assume that work is minus PDV. So this would be a constant pressure work, constant pressure expansion work, not a variable pressure. Don't get those confused. So we're going to assume that based on our first law of thermodynamics, we're going to sub in Q for dH, and we're going to sub in minus PDV for W work. Okay, so again, we're just going to insert these variables into this equation. So we can write change in internal energy is dH minus PdV. Okay, Q is dH, so it goes in here. Work is minus PdV, so it goes in here. And we're also going to make another statement, and that is that TdS is dH. Now if we take both of these expressions and essentially we're just going to sub in TdS over here, then we can have du is dH, where dH is TdS, minus PdV. I'm going to call that equation 3. Okay, so we have equation 1 up here, which I'll box. Equation 1 up here, equation 2 we have down here, and equation 3 we've just seen down here. On the next slide, we're going to combine these equations to gain some insights into dG. So here we have the three equations from our previous slide. Equation 1, dG is dH minus TdS minus SdT. Equation 2, dH is du plus PdV plus VdP. And equation 3, du is TdS minus PdV. We're now going to take these equations and essentially we're going to combine them all together. So the first thing we'll do is we'll insert equation 2 into equation 1. So as you can see, equation 2 has dH. So dH is equal to all of this material. All of this material is now going to sub into that variable here. So we've got, now this is fiddly, so we have to be careful we don't lose anything. So we have dG is dH, where dH now is du plus PdV plus VdP. And then I've still got this material here, so minus TdS minus SdT. Let's call this equation 4. I'm now going to insert equation 3 into equation 4. And as you can see, du is this material here. This material is now going to be subbed into this spot here. So finally we're going to get dG is du, where du is this stuff, TdS minus PdV, and then all of this material plus PdV plus VdP minus TdS minus SdT. So we have a lot of similar sounding terms, and we can definitely start to cancel like terms. So immediately I see I have a plus TdS and a minus TdS over here, so they can be cancelled. I have a minus PdV and a plus PdV over here. So the only terms that survive are dG equals VdP, and then this final term minus SdT. So they are now the only two terms that survive. So what have we learned? We've learned that Gibbs is a function of pressure and temperature. So if we vary Gibbs, volume is not varying, so it's not a function of volume, and entropy is not varying, so it's not a function of entropy here. But what will vary with Gibbs is pressure and temperature. So we've learned that G is a function of P and T, pressure and temperature. So we're going to take one of these, we're going to take this equation, and in the next slide we're going to produce one of the fundamental equations that you'll need in a general chemistry thermodynamics sequence. So picking up where we left off, in the previous slide we arrived at this equation which says dG is VdP minus SdT. So we can see that Gibbs free energy is a function of pressure and temperature. So we've learned something useful. Now let's see if we can manipulate these equations again. And to the student looking at this thinking, you know, how would you know to manipulate this equation further? How do you know you haven't finished? The answer is you don't. Historically, you know, it's human nature to tinker around with things, and 99% of the time you're wasting your time, but now and again you'll notice that that specific manipulation led to something useful. So whenever you look at a sequence like this where the answer is well known and anticipated, don't think that it's obvious that you should continue. You're just looking at what worked without going through all the tedium of what doesn't work. So I wanted to make that student PSA. Okay. So if we consider dG, we can say that the total change in Gibbs free energy, if we write this as an expression, it's the sum of the partial changes in Gibbs free energy. So I'm just making an expression that the total equals the sum of the parts. The total I've written with a regular D, the parts I've written with an italicized D, a fancy D, a partial D. So the total is the sum of the parts. That's a reasonable expression. And I want to vary the parts. What can affect these parts? What can affect these parts are the functions of G, which are pressure and temperature, which we identified earlier. So I want to look at the effect of pressure on Gibbs, and I want to look at the effect of temperature on Gibbs. So we're building this equation up slowly. Our numerators, we just had the total as the sum of the parts. I need a denominator because otherwise I haven't learned anything new. It's a barren equation. But now I want to look at the relationship between, or the effect of pressure on Gibbs. Why? Because I know Gibbs is a function of pressure. I want to look at the effect of temperature on Gibbs. Why? Because I know Gibbs is a function of temperature. The problem is I've killed my equality now, because there's no mention of pressure here, but there is a mention of pressure here. And there's no mention of temperature here, but there is a mention of temperature here. So essentially, I need to put something here that would cancel the effect of pressure, or at least would acknowledge the presence of pressure. So the way you would do that is to put parentheses around here and put dP, and we acknowledge that we've kept this variable constant while we're just looking at this variable. So we have constant temperature. And then likewise, we would put this term in parentheses. We fix pressure now because we're varying temperature. So constant pressure. And I'm looking at this ratio as I change temperature. Okay. So now we have a real expression. We're looking at Gibbs free energy. It's pressure dependent. Let's not change the temperature while we look at the pressure dependency. And it's also temperature dependent. Let's not vary the pressure while we look at the temperature dependency. Through an analogy, I know that this parenthetical term must be volume because I've got VdP, parenthesis term dP, so this whole thing must be equal to V. And likewise, I've got my dt here, so this whole thing must be equal to negative entropy. So I've learned that volume is the partial change in Gibbs free energy with pressure at fixed temperature. And I've also learned that negative entropy, or if you like positive entropy, is the negative change in the partial Gibbs free energy with temperature at fixed pressure. Okay, the next screen we're going to take this expression and we're going to move forward to produce one of the very fundamental equations. That we'll need in thermodynamics at the general chemistry level. Previously, we arrived at two equations. This is one of them. This is the one that we said that we would use moving forward, at least initially. So we've got a way of looking at volume. Volume is the ratio of Gibbs free energy change as pressure changes while holding temperature fixed. We can write this as a single line equation by just multiplying throughout by dP. So we can say that the change in Gibbs, change in general in Gibbs, so I'll revert back to regular D, is volume times by the change in pressure. So all I've done here, I've just moved the dP up here. So in general, if there are no other considerations, then we can just, rather than use partial considerations, we can just use regular considerations and say Gibbs is the product of volume and pressure change. Let's apply this to a liquid and a gas. So for a liquid, phase, we could say that the change in Gibbs free energy of the liquid is equal to the volume of the liquid multiplied by the change in pressure of the liquid. Let's call this, actually let's not call that anything yet. So we could say dG liquid. We should probably spit out what dG would look like here. So this would be Gibbs liquid minus Gibbs standard liquid. So I've introduced this term here. So we know that the change is going to be a difference, but specifically I want it to be the difference between the non-standard value and the standard value. This will become apparent as we move forward. For now, it's just a statement that that's how we would consider it. Here, standard just means standard conditions, so 25 degrees Celsius is the major condition. So the change in Gibbs free energy is the volume of the liquid, so that's just VL, And then the change in pressure of the liquid, again, we're going to look at the difference between the unstandardized and the standardized value. So the pressure of the liquid minus the standard pressure of the liquid. So that's how we'll consider it. And let's call that equation A. And we're going to do the same for a gas. So again, we're just going to use this equation. The change in Gibbs free energy of the gas phase is the volume of the gas by the pressure change of the gas. So we've got the Gibbs free energy in the gas phase minus its standard value in the gas phase is equal to the volume of the gas, or the volume in the gas phase. But rather than write volume, we're going to normalize it to 1 mole, and we're going to assume ideal conditions. So PV is nRT. N is 1 because we're assuming 1 mole. We're going to normalize this to 1 mole. So we've just got PV is RT. So V is RT over P. So V of the gas is now RT over P of the gas. So we've just substituted that in here. And then we've got P gas minus P standard gas. Let's call that equation B. It's nice to look at liquid and gas because now we can look at a phase transition. So let's consider phase transition liquid to gas. So if our final state is the gas and our initial is the liquid, we want to consider equation B minus equation A. So equation B is our gas, equation A was our liquid. We're going to take the difference. So we want to subtract relevant terms from A from equation B. So we've got Gibbs free energy of the gas minus Gibbs free energy of the liquid. So that's this term minus that term, and then we take this term minus that term. So minus standard Gibbs energy in the gas minus standard Gibbs energy in the liquid. So that's this term minus that term. And that equals this term minus that term. And I've just noticed there should not be a negative sign here. So that was a typo. There shouldn't have been a minus sign up here. So glad we caught that one. Okay, so we've got RT over P gas minus P standard gas. So that's the term on the right for equation B. Now we're going to subtract the term on the right for equation A, which is volume liquid product of pressure liquid minus standard pressure liquid. And we can start to simplify this up a bit. We know that the concept of pressure only applies to a gas. We can safely assume that the pressure of a liquid is negligible. So this is going to be 0. So this whole term is just going to equal 0. Again, because the pressure change in a liquid we assume is 0. So we're left with this term. This term just becomes dg, change in Gibbs, minus this term becomes a change in standard Gibbs, let's take RT, let's pool this P over with these P terms. This becomes dP, and then I'll move this P over here. Okay. So we'll leave this slide with that equation, and we'll begin the next slide with the same equation. We left off in the previous slide with this equation, which is dg minus dg standard is equal to RT, and then the product dP divided by P in the gas phase. But we want to move forward to an equation that sums over some of these d values. So these d's are infinitesimal changes. Individually, they're not that useful, but if there are lots of them, we can get some kind of holistic idea by summing over these little changes to see what the net change is. So we could write dg minus dg standard is equal to RT, and then I'm particularly interested in this form here. We've seen this before, where we essentially have a change in a variable as the variable itself changes. That's going to invoke a log base function to appear. So we want to sum over these changes. So I've essentially got the sum of over 1 over P in the gas phase, that's our denominator term. As P is changing, and I want to sum it between the phases. So my transition here is between the liquid and the gaseous phase. And recall that the sum of 1 over x as x itself changes is log base e of x. So this is a fact that we've seen before that we'll be using frequently in general chemistry. So this implies that this expression here, which we're just going to write as delta G minus delta G standard, at least we're going to make it look like it would appear in a typical textbook, is equal to RT log, because of this aside in the box here, and then it's going to be P over P standard. Because remember, when we took a change in P, it was going to be remember that this dP was the P under non-standard conditions minus the P under standard conditions. And recall from some log rules that if you to log both sides now, so log P minus P standard, which we're going to do, then it's going to be log it's going to be the difference. The difference, if you log a difference, you take the ratio of the logs. So that's just the log rule. So applying that here, we end up with this expression over here. So if we take our equation, which again, remember, is just a version of the second law. So we haven't looked at anything new today other than the second law, just manipulated to be applicable in different situations. We can start to acknowledge that this thing here, this is just a quotient. So let's call it Q. Quotient just means fraction. So we can write dg minus dg standard is RT log Q. We can take the negative dg standard over to the other side. So we can write dg is plus dg standard plus RT log Q. And this is one of the fundamental equations that you'll need in general chemistry, thermodynamics content. And we can take this one step further. We can consider equilibrium conditions. So we could consider at equilibrium, we know that delta G is 0 by definition. So delta G is 0 at equilibrium, and we know that Q is equal to K at equilibrium. So with this fact, we can now rewrite this fundamental equation. So we've got 0, because delta G is 0, is delta G standard plus RT log K, because Q is now equal to K. So we can rephrase this by taking all of this material over to the 0 side, and we can solve for delta G standard. So both of these final boxed equations are fundamental in thermochemistry or thermodynamics at the general chemistry level, and you would be expected to solve problems using these equations. So on the previous slide, we arrived at these two fundamental equations, both for the non-standardized Gibbs free energy change and the standardized Gibbs free energy change under non-equilibrium and equilibrium conditions, respectively. The final piece of this video will be to connect this with equilibrium using some nice visuals that you'd be well advised to scratch down during an exam as a visual aid. So I've got a plot of standard Gibbs energy versus reaction coordinate. And we're going to look at three components of these graphs, which essentially are slopes. So we have, let's call it a slope here. I'm going to call that slope C. We have a slope right here at the saddle point. I'll call that slope B. And we have this initial slope here, which I'll call slope A. So slope A, B, and C on this first diagram here on the left. So notice slope A is negative, slope B is 0. So we can see that slope A is a negative value. Slope B has 0 value. And slope C is a positive value. Okay, now we're going to put a test object in here. Let's imagine we put a marble. A test object, you want to probe a space, put a probe into the space. Let's say we put a marble here. The marble, if left to its own devices, would roll down, and then it would essentially slosh around, but ultimately the marble would end up down here if left to its own devices. Likewise, if we put the marble up here initially, the marble would roll down, slosh around, but ultimately the marble would end up here, left to its own devices. If we put the marble here, nothing will happen because there's no slope. So from Newton's second law, we know that force is mass times acceleration, and we also know that forces act on gradients. There is no gradient here, so there are no forces at play, but there are gradients at slope A and C position, so there will be forces at play. So where our test object will not move, at that specific location, that's our equilibrium constant K. That's our position of equilibrium. Notice that anywhere else we were to put our test object, so let's say anywhere here or anywhere here, well, this would be Q. And we know that Q always tends towards K, just as the marble would always tend towards the bottom of this gully here. So this would essentially allow us to ask Le Chatelier type questions. You know, if the marble was here, we would have a shift to the right. If the marble was here, we would have a shift to the left. Now, importantly, we're talking about marbles, but really we're not talking about marbles. Really, we're talking about equilibrium position. The position of equilibrium. So every time I say marble, here equilibrium position, and that's what's shifting. Okay. But ultimately, Q always becomes K. The marble always ends up at the bottom of slope B for the same visual reasons. Let's quickly annotate this graph, and you'll see the same idea. So we have slope B. We have a positive slope C. We have a negative slope A. You'll notice the only difference in my slopes, let's quickly put the equilibrium position in again. Let's put our test object, our marble. Anything to the right of K is Q. Anything to the left of K is Q. Q always tends to K. The only real difference in these objects now is I have slope B further right on my reaction coordinate axis, and here I have slope B further left in my reaction coordinate axis. So let's say if I were to look at this reaction coordinate and I said that, if I actually use the right notation, which is a single-headed arrow for equilibrium, not a double-headed arrow. Double-headed arrows mean reversible. Single-headed arrows mean equilibrium. Let's say these are the reactants and these are the products. Let's do the same here for our reaction coordinate. Reactants and products. Then we can see that the way I've drawn the diagram, my slope here my equilibrium position is on the reactant side. So I would say that this diagram favors reactants. Because I've got the slope on the reactant side of my reaction. And here I've got the slope on the product side. So I would say that this diagram shows that the system favors products. So it's important not only that you can interpret these diagrams, but they become a great study, a great visual aid when you're doing an exam. You have some scratch paper, you can sketch one of these down, and you can use it as a visual aid to the more abstract ideas going on with equilibrium and Le Chatelier type questions. And that will conclude this introductory video on thermochemistry topics for general chemistry students.